Hello, good morning, everyone. Hello, good morning, everyone, and welcome to our session. As you must have seen in the schedule, what is the plan is that by the end of this month, we will wrap up all these talks, etc. And the final two sessions which we'll have in the month, in that we will list all the possible projects, etc. And then the month of December is meant for people to actually work on their projects. And then in the month of January, right, sometime by mid-Jan, we will have a day when I mean, 1 or 2 days when all of you all can present what you all have actually done in your projects, right? Because then we are just, pouring in too much of information onto you all. And by then we think that it is time that you, digest all that information. So that's what we are going to do. So the next 4 weeks, 3 weeks rather, we'll have sessions of our own. And then after that, we will list the projects like I mentioned, and then you can start working. Yeah. So that's what we are going to do. So today I'm going to start with a talk on Gaia, because now the next 3 sessions, weekends, which I have, I will be talking about Gaia. So we'll be talking about statistics essentially, and astrostatistics, and therefore I'll talk about Gaia. Now I have done quite a few Gaia talks. There is also a resonance article which I have on it. So I will provide you all the links to that, as well as even the link to the other talk, because I don't want to repeat all that content today, right? So I'm going to repeat a few of the salient features, but otherwise I request you to all see that video. I'll give you all the link to that, and you can have a look at that video, right? So what we know is that to understand something truly, what you need to do is to measure it precisely, right? And basically, astronomy is a data-driven science, in the sense it depends on the flow of data, and that's the kind of interpretation and the theories you can have. And with insufficient data, it's easy to go wrong. So we later on be talking about this, about all the new developments that we have found out using Gaia, which actually quite contradict what was our earlier perception of our galaxy, right? So we'll actually see how our perception has changed. Now, one thing which we always need to remember is that the universe is a dynamic universe, okay? And it's constantly in motion. So therefore, when we get astronomical pictures, these are just snapshots, right? For example, look at this image over here, which you can see. Now, all of these are they are essentially stars, and therefore, depending on the shape of this galaxy, these are it's an interacting galaxy. What you can actually see is that it basically shows you the orbits of the stars, right? And those orbits are what you are catching in this snapshot. And therefore, when you're trying to understand it, you need to understand the kind of orbits that are there, which can actually get stars to give you forms of this kind. So initially, how has been our growth of knowledge that we had in our understanding of the universe? Initially, what we had was our study of 2D positions, right? That is, you look up at the sky, you see 2D positions, you get some kind of star counts, right? The next development which we had in our understanding was when we realized that the universe that we're looking at in the sky is basically a 2D projection of a 3D universe, right? And therefore, that came in the concept of parallax. We've already spoken about parallax earlier. But parallax is our simplest distance indicator, right? For example, our eyes itself constantly use parallax as a distance indicator, with the baseline being the distance between two eyes, right? The next thing what actually came in was studying of parts of the sky, which was, say, earlier studied with photographic plates. You actually compared the position of stars studied with photographic plates with the positions, say, with a long baseline, for example, a baseline of, say, 50 years or 100 years. And using that, people studied what were called proper motions. By proper motions, you mean to say the individual motions of stars, right? Now, this thing developed further, where you had now proper motions. So you had position in 2 dimensions, parallax 1 dimension, 2 more dimensions for proper motion. And then came the 6th dimension, which was radial velocity, right? Which basically came through spectroscopy. Through spectroscopy, if you study the spectrum of an object, you can get its radial velocity, right? And then based on that, indirectly, we determine all other astrophysical parameters of the stars. So last time, if you remember, we spoke about the HR diagram. So if you have, for example, you have the brightness of a star and you have its distance, brightness in two filters, you can directly place it on the HR diagram, and with the basis of that, you can get all other astrophysical parameters, right? So, yeah. So here, Gaia is basically an astrometric instrument. Essentially, what it's doing is astrometry. And what is astrometry? Astrometry is the precise position or movement of stars. So here you can see this, what I'm showing you over here is a very recognizable constellation, which is the Big Dipper. You can see this is what it was in the past if you take the individual conditions. And now you can see what it's going to become in the future, right? So the Big Dipper is just a constellation. It's not a cluster of stars. In the sense, the motion of stars are not related to one another. So all the stars, you see, this is way back in BC. This was the original shape of the Big Dipper. Then present time just ran through, and then now this is the future. Because all these stars are moving separately with their individual motions, right? And therefore, you can see that this constellation is going to change its shape as time progresses, because each individual star has its own individual motion, right? But astrometry is the precise measurement of the position and movement of stars of and other celestial bodies, right? And why is that important? Because that actually provides information on the kinematics and the physical origin of the solar system, the Milky Way, etc. So once you know the change in positions, you can determine the velocities, you can determine many more parameters for these objects for which you are observing and getting their these things. Right? Yeah. These could be near Earth objects which are part of the solar system, or they could be further, right? So now the question is, what kind of astrometry do we actually can we measure, right? So typically, you know, just for comparison, I've put these comparisons over here. That, for example, if you are actually looking at a second of arc, right? A second of arc, that kind of an angular size is the size of a rupee coin or a euro coin viewed from a distance of 5 kilometers. The new rupee coin, not the old one, the new one, at a distance of 5 kilometers, that is about the size of a rupee coin. 1,000 of a second an arc is the size of an astronaut on the moon as viewed from the Earth, right? And you can actually see that here, these are just comparison scales to actually tell you what is the kind of astrometry we are talking about. So if you have 1,000 of an arc or a milli arc, right? This is like viewing a golf ball in New York viewed from Europe, or for example, the diameter of a human hair seen from 10 kilometers. It's a very small angle. And even smaller than that is what Gaia tries to get, is in micros arc seconds, okay, which is corresponding to one Bohr radius viewed at a distance of 1 meter, right? So this kind of precision that we are talking about is crazy. It's really very, very high precision. Now, astrometry, the way our development has happened in the study of astrometry, you can see over here, this is Hipparchus, right? Which is actually, which is naked eye observations. This is CHUS, okay? This is naked eye observations of various people. How is that improved? And then you can see this jump over here. This jump comes basically because you start doing astrometry from space. It was realized that if you're doing it from the Earth, the atmosphere obviously gives a very large hindrance. So if you're observing from space, your precision is going to be far more better, right? And therefore over here you have Hipparchus, which was the first satellite which was sent to do astrometric measurements. And now you have Gaia, okay? So the precision in the, so here you already going into milli-arc seconds. Here with Hipparchus, you're going to micro-arc seconds, right? With Hipparchus. Now there are various catalogs already available on the net, which actually give you the kind of, a different kind of precision or the movement, the proper motions in different catalogs, right? We won't go into those details, but we'll talk a little bit about stellar motions. And I would like to show you all this thing. I hope I can show that to you, and I will 1 second. I'll just show that, just a minute. I'll just show that to you. And what I want to show that if you are actually looking at the sky, right? 1 second. I'll show you this thing. Uh, 1 minute. So I will. I'll just close this and just give me a minute. I'll show it to you. And here you can see. Okay, yeah, here. So I'll just show you an image of, for example, if you look, I hope you all can see this.
Yes.
Can you all see the video?
Yes, yes.
Yeah. So here you can look at this. This is an easy thing showing you what is parallax. Look at this. This is just a part of the sky. Okay. Now, if you remember the part of the sky, we already spoke about parallax, that if you're looking at the position of a star, since the Earth is going around its own orbit in a year, every star will do an ellipse. Okay. It will kind of loop because it loops in through the year. But the amount it would loop in would depend upon the distance as well as the velocity of those stars. So look at these stars over here, and you can see that all of these are tracing circles. There is one which you can see it more bigger, but all of these you can see are tracing circles. And these are the circles of parallax, which are changing in a baseline of a year, right? So you have this looping in taking place, which is happening in the period of a year, right? So I'll show that once again to you. This is the kind of loop which you're going to get because of parallax. So if you look at a position at a part of the sky all through the year, you will see this kind of a movement coming from the stars, which is coming because of parallax. What is not embedded in this is that you will also have a certain kind of motion, which you will have because of individual motions of the sky, right? So I'll go back to that and I'll show you that. Okay, here. So I'll come back here. I hope you all can see this slide of mine. So we already spoken about parallax earlier, where parallax we said is the motion which you're getting through the year, right? Because of this loopy motion which is happening off the stars, right? Now, parallax is, we've explained it earlier, and parallax gives you a distance in principle. The distance in parsecs would be 1 upon pi, which is the parallax. How far do we measure parallaxes? So here I have a mention of Hipparchus and Gaia, right? So like I mentioned earlier, that there's a big advantage of going out in space. The kind of accuracy which you're going to get is amazing because of you going into space. Because then you can have an all-sky coverage. The spacecraft is relatively stable, temperature, gravity invariant, etc. Right? So in that way, what Gaia actually does is what is called absolute astrometry. Okay. Now, Hipparchus, I won't go too much upon it. I actually urge you all to see these other videos, which I'll give you a link of. Nehru Planetarium, the planetarium in Delhi. Okay, they were running a series called Astro Adda. Okay, so I started off that with a talk on Gaia, so I have 2 Gaia talks in the Astro Adda. I'll give you all the link to that, and you all can use that to see these. So I'm going to jump through this thing. So what you have is proper motions, which we'll be measuring, which gives you the transverse velocity and the radial velocity. Okay. And with that, you can actually get the space velocity of a star. So what is actually going to happen is, one motion I showed you was the parallax motion, the loopy motion. The other motion is the proper motion, that is the movement of the star. And therefore, if you have the combined motion of it, you will have loopy motion like this, which is moving like this. So in the motion of the star, there are 2 things. One is the parallax and one is the proper motion. In case the star has a planet, then you will again get a wobbly motion, right? So when you're actually studying the motion of these stars, you can actually get this wobbly motion also. So in principle, by studying this motion, you can also look for exoplanets. For example, if there's a star which has its own planet, it's also going to show you some kind of wobbly motion. I hope this picture is also clear in your mind about proper motion and radial velocity giving you the true motion of stars. So like I mentioned, going up in space gives you an advantage of the twinkling, blinding effects of the atmosphere, etc. And Gaia was launched over here. So you have, it basically goes to the L2 point. right? So you know there are 5 Lagrangian points for the Earth-Sun system, for any two-body system. And this one is the point which will always be shielded away from the sun, right? So here we have the L2 point. Here's where Gaia is. So if this is the sun, this is the Earth. These are all the 5 Lagrangian points, which are the ones where you have equipotential surfaces. And L2 is where Gaia is sitting, which is a distance of about 1.5 million kilometers, right? And it kind of hovers around the L2 point over here. It's not static. It kind of hovers around, and it goes around in this way, right? Now, so what basically has is your Gaia has two mirrors, which are at an angle of 1.6.5 degrees. Okay. The idea in this design, I won't talk about it too much today, but it's basically the idea is it gives you, you're getting double images, so you can use it. It is used for the astrometric calibration because you're looking at the same object through both these mirrors, through which you know what you have is the angle is fixed. You know what the basic angle is, and that is actually used to very well get absolute astrometry, right? So you have these two telescopes which are over here, and they are observing. And so, like I said, it's in the Lesagos orbit. It was launched in 2013. It has already finished its 5 years, and now it has its on what is called an extension period for another 5 years. And what is basically done on this thing is here's the telescope. Here's the telescope. Here is the what it looks like. These two telescopes, and you have various instruments which are kept over here. And what is basically done? So what you have is on the focal plane. So one thing you need to know is that this is basically doing many motions. One is it spins. It spins in a period of 6 hours, right? The axis also precesses in a period of 63 days. And since it's on the L2 point, it revolves also in 365.25 days because it's going around with the Earth, right? So when one is studying the motion of or the measurements which you're getting of stars from the satellite, one has to consider all these extra motions which are also part of the satellite motion, right? And what was done, it was launched in 2013, and by 2014, they started routine operations, right? Now, so what you basically have is you have this huge set of a billion pixels in the CCD, and here's the CCD put over here in the focal plane. What you actually have is the photometry. We won't go into too much of those details, but basically what is done is the movement of a star is scanned. Okay, it moves through the sky, it gets scanned. And the photometry means we measure the fluxes in one band called the G band, and in two more bands, one is the GBP, which is the blue photometer, and the GRP, which is the red photometer, right? So this is used to actually measure the thing. This video of mine is not working. And you also have a spectrograph, radial velocity spectrograph, RVS, which is measuring the radial velocities of stars. The only problem with this is that spectroscopy, like I told you all earlier, works well only with very bright stars. And therefore, this works till about 14, 15 magnitude. It doesn't go fainter than that. So you're getting this astrometry. I don't want to do too many things about this. There are many interesting things to understand about why do you have two telescopes and how does that actually do the job of astrometry. Now, what is basically done is that when the telescope gets the data, right, it does a very simple amount of analysis on board, right, on the satellite. The rest of the information is directly sent by telemetry back to the Earth, right, to the ESAC centers. And then what is done is that there is a very big elaborate job, which is the job of getting the end product, which is got out to people, right? And that is done basically using something called the DPAC, okay, which is the uh, processing unit. Okay, so what happens is the data comes down straight, but is beamed back to the Earth, and then it has to be processed before it is actually given out to the community, right? And this is all done by a very big group of people, which all work under ESA, the European Space Agency, and essentially it's in Barcelona. And what they do is that they process the data so that it is in a condition which is good for everybody to use. There's more about this on that Astro talk of mine, where you'll find details about the various things which are to be studied. So what you have to actually keep in mind is that the astrometry works for G magnitude brighter than 20 magnitude for about 1 billion stars. Photometry, like I told you, you have it in 3 bands. One is the G band, which is a very broad band. And then you have 2 narrow filters, which are the red and the blue filters. Radial velocity in principle is less than 16th magnitude, but most of the time you won't even find it for all 16th magnitude objects because there are other factors which would play a role. So you can actually see that Gaia is a major jump over Hipparchus in the kind of precision, etc., which you are going to get with it, and the kind of topics which it can deal with, right? So, like I mentioned, exoplanets, studies of the solar system, spectroscopy, and some Gaia numbers. I won't go into those details. Now, what I want to get you all to is something. So, if you'll remember when we did TopCat, right? So, how would you actually access data, right? So, let us see how do we access data. We access data essentially through. I can show you 2-3 different sources, and we will talk about those. So, for example, if I were to show you, let us go to. No, I want to. 1 minute. I'll just get into Chrome. I think I've closed my Chrome. So I just open Chrome. Yeah. So here now what you see is I'm going to now show you how do we actually access the Gaia data, right? So if you'll all remember, there was a time when we did TopCat, right? So one of the simple ways of accessing our Gaia data is through TopCat, right? So I don't think I need to repeat that. Should I repeat that with people or no need? You can go through the TopCat lecture and see how you can actually access data through TopCat. The other way that data is accessed through is through something called Vizier. Okay, so we already spoke about Vizier when we spoke about this. Yeah, so let us look at this. So what you actually have, if remember I told you all there are different astronomy data sources. So Vizier is a service which is provided by astronomy community, okay, which is run by CDS Strasbourg, okay. And Vizier, what it basically does is it gives you access to publications as well as data, right? So if people published using data, you can get that data, as well as you can actually get catalogs, etc., right? So for example, if you go on to Vizier and you just type Gaia, okay, and let's find with Gaia, it will actually tell you all the catalogs it has which are related to Gaia. So for example, you can see over here, there was an earlier data release of Gaia which was called DR1. So this is Gaia DR1. You can access that data here. There's Gaia DR2, which is over here. And next month, there's a new data release which is going to come of Gaia, which is called the EDR3. Okay, so it's a data release 3, but it is the early release. Okay, it's the early data release. And later on in 2022, early 2022, there will be the DR3, the full DR3. But what's going to happen next month is going to be the early DR3, right? So here you can see various catalogs which are there which relate to Gaia. So for example, if I click on this, this is the main DR2, right, which is available over here. I can click on this. And here you can see there's the listing of all the data. So for example, this one is the DR2 with all the releases. There are sub catalogs within this. This one is for radial velocities. You can read all this, which actually tells you what are the different factors. So let's get into the basic catalog, which is this one, which is the DR2 release. And this is a very simple way of accessing the data. So for example, if you have a cluster or you have any part of the sky, over here, you can even give the RA deck of that object, the rise ascension declination, or you can name the object. For example, you can name NGC 1960. This is a cluster. So for example, I can give NGC 1960. I can say what area I want around it, say 20 arc minutes, supposing. And here what you can see is these are all the columns which this can deliver you. So the RA, the errors in the RA, if you have any doubts about this, you can always click on this. It will give you more details about those things, right? So these are all the units, the unit it's going to give it in. This is the parallax, error in parallax, RA, dex, etc. All these are given to you over here. There are various other factors. Now you can see that not all these columns have been clicked. Okay, only some of them have been clicked, and this is the default setting. But if you want to add more columns, right, you can actually add it, right? Now, what is very important for you all to notice is that the parameters which you're getting from Gaia, right? It's essentially the right ascension, the declination, the parallax, the there exist correlations, okay? And you can see these factors given over here, the correlation between right ascension, declination, right ascension, parallax, etc., right? So these are all, it's the way the data processing takes place. It's very important to actually understand very well how are the errors and the correlations done between different parameters. Because here what you have is you have a very accurate data set, right? And if one misinterprets the data, it can lead to many wrong interpretations. And therefore, I urge you all to actually, uh, what is important for you to go is to go to the ESA Gaia page. Okay, the ESA Gaia page, and this actually is, ESA is the European Space Agency, the Gaia page, and this is a very good repository of various things about Gaia. I will not continue talking about it, but you can have a look. The ones who are going to do Gaia projects, it's essential that you go through the page over here, and you actually see the descriptions, etc., which are given about the data set, etc., and what about the errors, etc., which are coming into this, right? And therefore, I urge you all to see this data page, right? We'll come back to it in a minute. I'll just finish a little bit about Vizier, and then we'll come back because there's something else also which is important about the ESA site. So what we are going to do is we'll go back to Vizier. So like I said, you can click on whatever extra column parameters you want and you can download it. Now, when you download it, you can even just, for example, there is a plain submit button. Okay, and that submit button will let you actually, it'll come on the screen. Okay, whatever is the data you've asked for. So a certain amount of columns, sample data, it comes on this screen, and you can see it over here. Yeah, so this is the columns and all which you've asked for, which are coming over here, right? This is an HTML format, okay? But it obviously gives you a choice of what are the formats you want to download the data in. So you can actually, this is only 50 columns. You can get it to unlimited if you want, and get it to various different data formats. Now, this is the VO table format, right? There's a fits ASCII table format. There are various table, there's plain ASCII table format. And all of them, you can download whichever one you want. Since these are in VO formats, so therefore what will happen is that all VO compliant tools will open it. For example, if you open it with Aladdin or you open it with TopCat, you can open a VO table, you can open a FITS table, all these things you can open it using any VO tools, right? Aladdin, TopCat, etc. These can also be used if you have a Jupyter notebook and you want to open with Jupyter notebook also. You can do that if you download any of these formats. If you want plain ASCII format or comma separated variables, all of them are also available. So you can click on that and it will let you actually save the file. So for example, if I take a VO table format and I say unlimited and I say submit, it can actually give me let me save the VO table format of a particular file. And that's how you can save your data and you will actually have the data, right? Fine. So Vizier is one very standard way of getting data. The other very good thing which one can do on data is that supposing there's a paper which you find interesting, right? Now, what is done in the common ethics in science is that results should be reproducible. Okay. So for example, if a certain person used some data to actually get certain results, he or she can upload the data on Vizier so that other people can reanalyze that data and get their results. So many of you all would be aware about the phosphine in Venus issue, which is on. And like I said, as per the normal ethics, the data is made available to the whole community uh, for to verify the analysis. And you all may be aware that there's already a group which has analyzed the phosphine data, and they have actually contested it. They are actually saying that the phosphine that was reported to be detected is actually from the mesosphere of our atmosphere itself, and they have wrongly identified atmospheric lines of the Earth to be the phosphine lines of Venus, right? Now, at present, if you're aware of it, what they've done is that they've just contested the results which the earlier group has given about phosphine, and it is kept to an open debate. So if you can actually have a look at it, it's done in a very nice way where you can reanalyze the data. Supposing, like in this case, the group says that no, this data has been wrongly calibrated, it has been wrongly done, and it actually does not imply what the authors say. So now they have asked the authors to contest with them, right? To have an open debate about whether their results are right or wrong, right? So that is a very democratic, nice way in which we deal with issues in science, where you can actually reanalyze data that people have used to actually check or validate, or in case if you think that they have made some mistake in data analysis, you can actually use it. So what happens in Vizier is that if you have any data, right, by some other author, right, you can actually look for that data. For example, if I come out of this and let us just look uh, for example, let me look for the same thing. So let's see if we go in for phosphine. Okay. So you have the phosphine data, and no, but this is another one. So this is not that one. But in short, you can actually go through the data of anyone, right? For example, let us take, for example, Vera Rubin, right? She made studies of dark matter, right? And therefore here, for example, you have various data of us. This is very good data. So for example, you can actually access the data which they have to actually reanalyze it and see if you think there is something more to the data, right? In the sense of the analysis methods, etc., right? So Vizier is a very good tool. It's a good idea to get aware of it. Now I'll come back to Gaia. So like I said, for Gaia, it's a very good idea to go through the website, right? And you can also access the data from the Gaia page, okay? This is using a language which is similar to SQL, which is called ADQL, right? I will talk about that later. But in short, the advantage in that is what? Now, you know that the Gaia data is a very large data set, right? And therefore, what happens is, supposing I want to do analysis, I can't download the whole data set on my computer and then sit and analyze it, right? So therefore, what is done is that you can actually access you can actually be, I'll show you how that's to be done. You can actually create an account for yourself on the website where the server is sitting, okay? So by default, they give you a 1 GB space, okay? And what is done is you can query the data at the server level. Instead of doing it at your local level, you query the data at the server level and then only extract the data which is of your use, right? So you can put various conditions or various things about the data you want to query. I will talk about that a little later, maybe not today, maybe next time. But you actually, I'll show you all how that's to be done so that you can query at the server level. And then you get the data so that then you can analyze it at your own this thing. But the querying happens much faster because you're doing it at the server. Now, the other part which I want to show you all today is ESA also did something called EsaSky, okay? And EsaSky is in a way similar to Aladdin, right? We already did Aladdin, which was a visualization software. And now we will, what I want you all to see is that I've got in touch with those people. They have been kind enough to actually give us the a short video on EsaSky, and that's what I'm going to show you just now. And 1 minute. One second, I'll just show you all that EsaSky video, and it basically shows you all how to do it, after which I'm going to give you all a homework, right, which would be actually analyzing and getting that thing. So I'm going to 1 minute. I'll just, I had already got this ready, but it has gone lost. But now I'll show you that short video, and you can have a look at that. So where is this gone? I don't know. I had already kept the thing ready, but it's not here. Okay, no problem. So I'll just show you all that video, and just give me a minute. Nacham, just say yes, no? Yeah, just a minute. I'll just I just need to just say that I'm logging in. Yeah, so I'll just yeah, so I'm going to now show you this short video, and I would actually urge you to actually have a look at the extra videos also which they have on the ESA site. Okay, so I will just show you this EsaSky. I kept it ready. I don't know why it got lost. No. No. Yeah, so here is the video that they've shared with us, and I will just show you all that in a minute, and then I will give you all a tutorial which you need to run, right? So let us just share this thing. Najam, I need to put this on. Are you all seeing my screen? Okay. Okay, so I will. Right. So, so you can have a look at this video, and Deborah, who's actually made this video, she can be available if we need some doubts or questions, and otherwise I will try to answer them. She's not logged in today, but we can listen. So please have a look at this video, okay? But for video, I need to do the other sharing. No? It's fine, fine. Okay. Yeah. Is it coming? Or? 1 second. So I'll say share screen.
I work at the EsaSky Science Data Center in Madrid.
1 minute.
Hi, my name is Deborah Baines. I work at the EsaSky Science Data Center in Madrid, and I'm the product owner of EsaSky. And I'm going to introduce you now to the EsaSky tool and to PyEsaSky, which is the Jupyter widget for EsaSky. This presentation is on behalf of the whole EsaSky team, in particular Bruno Merin, Fabrizio Giordano, Elena Racero, Henrik Norman, Matthias Vanblad, and Marcos Lopez Caniego. One of the reasons we developed EsaSky is because we were being asked by the users of our archives to create a multi-mission and multi-wavelength interface to our archival data. Now, this image that you see here is a word cloud made up of all the feedback that we received regarding the type of application needed. And as you can see, it's the data that is of most importance to our archive users. So we developed EsaSky, which is an interface that lies on top of all the ESA astronomy archives and archives from other partner space agencies and large data centres. The tool doesn't replace the archives, but instead provides a different type of access to the data via an all-sky exploration interface that is multi-wavelength and project agnostic. The first public version of EsaSky was released in May 2016, and our latest release was about 3 weeks ago, where we released EsaSky in the Chinese language. So the tool is now available in English, Spanish, and in Mandarin. We know that a large percentage of the astronomical community are now using Python and AstroPy, and we also see a lot of queries being made to our archives via their AstroQuery modules. So we decided to create an EsaSky Jupyter widget, which we've called PyEsaSky. And with this widget, you can upload your own data. Currently, these are tables, footprints, and HIPs, hierarchical progressive surveys, which is what you see in the background of EsaSky, which I'll show you now in the demo. And you can also download any data found within EsaSky. Plus, you can interact with the EsaSky functionalities, such as the search, the background HIPs, the James Webb Planning Tool, the field of view, the grid, etc. So now I want to show you how EsaSky works in a demo, so let me switch to my browser. And here we have EsaSky. When you first open EsaSky, you see this welcome box. We have two modes, Science and Explorer. I'm going to show you the Science mode today, which provides you with all the scientific functionalities available in the tool. So EsaSky is an exploration style interface, as I said, and the entire sky here is available for you to search and explore. So you can zoom in and zoom out and pan around. Over here we have the search box, where you can search for any astronomical target, any solar system object, and you can also search by author or bib code and see the associated sources for a given author or paper. Now I'm going to go to the Horsehead Nebula. So here we're looking at sky, background sky in the optical with DSS, and you can change these background skies if you click on this first button here, and you can select via wavelength many different HIPs. So these are hierarchical progressive surveys that we're showing in the background. So let me open up, for example, in the X-ray we have background HIPs from XMM Newton. In the optical we've got the DSS2, we've got many others. I'll also open up the near infrared, the mid infrared from All Wise. Let's open up another one that's from Spitzer, and let's open the far infrared from Herschel Pax. And you see that we have this slider here along the bottom, so you can start actually play through all of these skies. Let's pause this, and you can also take a hold of the slider and pan through yourselves. So if I go back to optical, now I want to show you how to find and download data. So these buttons over here with the numbers are showing us how many imaging observations are available in this region of the sky, this rectangular region. It also shows us how many catalogue sources are available and how many spectra are available. So these three buttons, we can access data, and also this fourth button here, which I'll show you in a moment. So let's first click on images. Here we see a tree map with the missions that have available data in the field of view of the screen. You can filter the missions by wavelength using this slider at the bottom. For example, if you're only interested in high energy, you could move this button along here, or perhaps you just want to see infrared to radio, then you can slide along here. If you want to find out any more information, then we've got these little help buttons with question mark all over. So you can click on this, it gives you information, and it sends you to a link for the full documentation. And clicking on any mission will bring up the data. So let's click on Hubble in the optical, and we immediately see the footprints appearing in the sky and also the metadata down here in the data panel. And if you can interact with the sky, so you can click on the footprint and the corresponding row highlights, or vice versa. You click in the table and the corresponding footprint will highlight. You can also filter any column. So let's take, for example, the instrument, and I could just look for ACS, and then immediately we see the results shown here. We have postcard previews that load up the postcard directly from the European Hubble Archive. And if you click on the observation ID, you open up the archive directly on this observation. This little icon centers you in the observation, so you can find where you are. So to download the data, either select one, a few, or all of the data, and then go to this download button here and click on data products, and you download the data straight away. So this is the same for all other missions. So if we load up XMM, it's exactly the same. We can see the postcard straight from the archive. We have direct links to the archive, so it will load up this observation. And you can download your observations as well. So download these two data products just with a few clicks of the button. The same for Chandra, and Chandra takes you straight to the Chandra archive in Harvard. So it's very easy to download by selecting the data you want and clicking on the download button. So let me close all of these, and I'm going to show you now the catalogues. So here we have the button for the catalogues, and you find a very similar tree map for all catalogues available. This can also be filtered by wavelength. Over here we have an interesting cluster by the look of things. So let's load up the Gaia DR2 catalogue. And since this is an astrometric catalogue, we are seeing the proper motions here. The proper motions are indicated by the dotted lines. If you zoom in a lot on a source, then you'll see that the dotted line will turn into a solid line, and that's the true proper motion. Here we are. So let's zoom out again. You saw as I was clicking that this option of going to other surfaces becomes available. You can also get that if you right click. So if you click on a source, you'll get that, and if you right click, you'll get that. So let's go to this object, for example, and see what it is in Simbad. So this looks to be like this young stellar object, HD 37525. And we have the parallaxes and the proper motions. They're all from the Gaia DR2 catalogue. So if I go back, we can actually start filtering what we've loaded, and we can filter on the parallax and proper motions. So let me filter parallax between 0 and 3, or between 1 and 3. The proper motion between 0 and 2 in RA, and the proper motion in DEC between -2 and 0. And now you can see all the sources with these proper motions and parallaxes within these ranges, but we're still seeing the sources that don't have any parallax or proper motions within DR2. And if you want to download what you've been filtering, and of course if you want to download any of the tables, just select all and click on the download button, and you can either choose a CSV or a VO table. So we can find out more about this star as well by selecting the publications icon. So this is this button here. When I press this, all sources with an associated publication are shown. So I can then go to this star, and we see that there are 63 publications. If we click on it, or if we select here, then we'll load up all of these publications. Now this is accessing the service provided by CDS, who have linked all publications to sources. You can again filter any column, so we could search, for example, for cluster, and here we can find out a bit more about this cluster. We can, if you click on any of the bib codes, then you'll open up the paper directly in ADS. And this little parchment button allows you to open up all of the sources in the publication, and you can start clicking through them, and they're all highlighted in by a green square. So let's go back to the region that we were in, and you can now see all of these sources. If you want to distinguish between the sources that you've loaded and the Gaia catalogue, we can, for example, change the colour of the footprints or of the sources. So here we go. Here we can see the Gaia sources now as well. And linking all of these services enables faster data discovery, which we hope your science can benefit from. Let me close everything again, and let me close the publications and these sources. And the third button to find data is for spectra, and it's very similar, almost identical to downloading and finding and downloading imaging. So let's, for example, we have access to LAMOST from the Chinese Academy of Sciences, and you can see a preview of the spectra, and this is coming straight from the archive in Beijing. And if you click on here, we go straight to the archive as well. So we can load up all available spectra within the region, and you can download it exactly as we've been downloading with the images and the catalogues. So you click on this button here. So we also have a fourth button to access data. It's this one here, and this allows you to explore data from other external data centers. The data hasn't been curated by us, but we're accessing these data centers. We're using the table access protocol, which is one of the virtual observatory standards that many astronomical data centers are using as one of the means to expose their data to the public. And currently this is accessing data from ESO, CADC in Canada, and MAST in the US. So if I click on ESO, you can see here all the different data types that you can search for, and this includes ground-based and space-based data, obviously. So we have spectra, images, visibility and measurements. So there are also cube data and time series available. So if I go to images, we can load up the ESO VLT images in this region. And this is still interactive, so we can select footprints on the sky and interact with the data panel. And if you want to download the data, you click on this access URL and you select the first one, which is the Science Ready Fits. Click on this and you begin to download the data directly from ESO. And then if I go to DS9, we can see that we've loaded this data up from ESO. And we can do exactly the same for the other data centers. So let's click back. And in MAST, let's go on cubes and select Swift. And for CADC, for example, let's take a look at Gemini spectra. So the Swift are already loaded. So we go to the access URL again to download the data, and it downloads directly for this mission. And for Gemini, we can center on the observations as well, and we download from the first link in the top. And in the near future, we are probably going to put all of this into fewer buttons to make it even more streamlined for you to find data. So everything will be a lot easier to find and a lot easier to download. So please do keep checking the latest versions of EsaSky. Now let's reload and show you a couple more features. So via this button here, you can upload your own list of targets. And for information on the format, just click the help button and you can go to the documentation. So let's upload a target list here. You see that it's just simply a list that can be resolved by Simbad or coordinates. And you can also add a description here. So if I open this, then if you've added the description in the file, it pops up here. And we also have a lot of other target lists, example target lists for you to take a look at. This button here opens up the observations planning tool for James Webb. So if you click on the plus button and you're given 5 instruments of James Webb, so select one and then you can select any of the apertures, and you can also click on all of instruments to see the full focal plane. You can change the RA and deck, and you can rotate, and you can do this manually here. And once you're happy with all of this, you can copy the coordinates and data, and then this tool is for a quick look on how you'd like to do your proposals before moving on to the APT. Now, if you want to see the full sky coverage of all missions, zoom out and start loading up the global sky coverage for all of the missions. So let's do, for example, Hubble, Herschel. Here we see the galactic plane, ALMA, XMM, Chandra. You see this is very, very fast and easy to do. And you can do the same for the spectra as well. And we can see regions that have been highly observed, like the galactic plane or the ecliptic plane, and we see other regions that have been less observed. And we're looking here essentially at the whole history of data taken by the astronomy space missions. So finally in EsaSky, I want to show you the solar system objects feature. So I've reloaded. In the search box, you can search for over 750,000 solar system objects, currently for 3 missions, Hubble, Herschel and XMM, Newton. And the EsaSky team have created a pipeline that calculates the orbit of the SSO as seen by the satellite and cross-matches this against the images in the 3 archives. So we have targeted and we also have serendipitous results. Let me show you an example. If I type in Psyche, we are given the option to search for the asteroid, and we're told that we have some Herschel observations. So when I click on this, we're zoomed out on the whole sky, and what we see here is the orbit of Psyche as seen by Herschel during its entire lifetime. And if we center on the observations, we can see them here, the footprints in the sky. We see that we've got 2 Pax and 2 Spire observations. Let me change the background hips now to Pax. And if we zoom in here, so we can see falling perfectly on the orbit. In the background hips for Pax, we see the asteroid appearing twice because the hips were made up from the 2 images. We also see this in the postcards as well, coming from Herschel. And these were not targeted observations, so the target for these observations were L1551, which is a dark cloud nebula. So these are serendipitous observations. Now, a NASA mission is going to Psyche in the 2020s, so these serendipitous observations by Herschel could help to refine some of the physical properties of the asteroid. And there will be a publication out soon by the team describing the SSO algorithm and the analysis of these Herschel images on this asteroid. So finally, let me take just a few minutes to show you the EsaSky Jupyter widget and some typical things that you can do in a Jupyter notebook. So this is a notebook open in Jupyter Lab. We have EsaSky open here, and you can find this notebook in the GitHub of EsaSky under the samples directory. This notebook shows examples of what you can typically do with EsaSky. In particular, you can download and inspect data from EsaSky. You can cross-match catalogues available through EsaSky. You can upload your own data, and you can interact with EsaSky functionalities. So I won't show you everything now. I will provide links to this notebook at the end of the presentation. And please also see our EsaSky e-poster that also has details. So if I jump down here where you can actually load up your own data. So we do a cross-matching of catalogues, and you can load up your own data in EsaSky. So this is sending a cross-match table to EsaSky. We can also send catalogues from Vizier, so loading up the AstroQuery Vizier module. And you can search for any catalogue and then load it back into EsaSky. So if you're interested in learning more about this, as I said, please see our e-poster and please check out the links at the end of this presentation. Plus, if you want to find out more information, you can go to the documentation within EsaSky. So just click here and you, for example, click on the video tutorials. And here we have many videos. We have a video of EsaSky as well. And we have links over here. For example, here's the link to the EsaSky widget and information on how to install EsaSky. So the creation of EsaSky isn't possible without collaboration, e.g. with other data centres. For example, with CDS, we are using their Aladdin Light tool to visualise the sky, and we're also using their astronomical name resolver Simbad and Sesame, and we're using Simbad to expose the sources with associated publications. We have worked with the AstroPy community, in particular AstroQuery, to create an AstroQuery EsaSky module, and of course we've created the Jupyter widget EsaSky. This allows users to do more sophisticated studies of the data. And let me emphasise that all of the interoperability you see in EsaSky is thanks to the International Virtual Observatory Alliance protocols, of which we are using many. And this is thanks to the international collaboration between astronomical data centres. So please try EsaSky yourselves. These are all the people and institutes that have been involved with the tool so far, and we welcome contributions from anyone who's interested, so please contact us. This slide gives you some useful links, and finally, if you have any feedback, contact us via User Echo, and please also see the EsaSky and EsaSky e-poster. Many thanks for your time.
Yes, so I hope all of you all enjoyed that video. It was obviously very one second. Huh? Yeah, but I can't stop it. Okay. I'm sorry for that disturbance which we got in. It just moved on. So, hello everyone. So, what I want to do now is obviously this whole thing about EsaSky was very power packed, right? It had a lot of things inside it. And therefore, what I'm going to do is I will stop here. I will not do ADQL, but I'm going to give you links, which are links to, I will, okay, I'll put it on Telegram. I can give you links to a short exercise, okay, which you can do on EsaSky. So I will put that now up onto your in the chat box. So in the chat box, you can see I will give you a thing that is there's a EsaSky short tutorial with Pleiades, okay, and I urge you all to try doing this short tutorial. And with that, a lot of things about EsaSky should get more and more clear, right? I also urge you all to, let me just do this. I will, I will urge you all to, let me get this thing on. Yeah. So the videos that I showed you, there are many more of them available. Can you all see my browser? Yeah. So the videos that I showed you, many of them are available on YouTube. There are much more detailed videos available if you actually check the YouTube site with EsaSky. Okay. And I urge you all to go through this. So it's very simple. You can just the good part about EsaSky is you don't need to download it on your system. You just say EsaSky on your browser and you can open it straight away like this, right? So you directly use it from your browser because it's Java based. And here you go into the science mode, right? So from your browser, go on to the science mode, click on science. And here, like Deborah mentioned, right? Here you have your various things. For example, this is optical DSS color. You can add to it, for example, your you can add whatever other things you would like to have. You can, for example, this is the HST ACS data. You can add that to it. You can add various data frames. So there is no installation issue at all with EsaSky. Directly use your browser. And with your browser, you can open EsaSky. You can see all the stuff inside it. And what Deborah mentioned over here also on the right-hand side, you can right-click and here get your video tutorials, etc., the feedback and all that. So you have video tutorials over here, newsletter over here. And you can see that what basically EsaSky is doing is that for a particular part of the sky, it gives you access to all kinds of data. So this is imaging data, spectroscopic data, catalog data. See, there are basically three kinds of data. One is the image, one is the catalog, and one is spectroscopic. So you can see all these three are represented over here. This is image data, this is catalog data, this is spectroscopic data, as well as the publications which are there on it, etc. Right? So here what you have, this also, this is for observation planning tool. This has been also provided by them that supposing if you want to observe a certain part of the sky, you can use this to actually very well study what are the observations that are there for that part of the sky in different parts of the wavelength, etc. What are the interesting objects for which do you have spectra, etc. And accordingly, you can pick up your sample which you want to use for observations. So this observation planning tool is also very good. It gives you some basic stuff for different telescopes. For example, this one is for JWST, the James Webb Space Telescope. So for the specifications of JWST, it actually tells you how could you plan observations for certain parts of the sky, right? Now, what is important is that one has to appreciate the amount of effort that has been gone in planning these tools, designing these tools, so that there is access to data and information for everyone, right? And Gaia, like I'm saying, we are going to be doing Gaia data, but Gaia coupled with other data sets makes it even much more effective. You know, if you couple it with different spectroscopic data sets, then you'll have chemical abundances. You can add it to, for example, if you add it to infrared, you can find out dusty regions, young stars. You can find out various other things. So that's good. So fine, I can already see questions listing. How can we account for the errors while cross-correlating Gaia data with other data? Say Fermi data, yeah. So that's a very good question, Aditya. The problem is that different missions or different wavelengths, different telescopes have a different error bar. the precision with which astrometry is available for them varies. And therefore, cross correlating is not a very easy job itself. It's a very complicated job because sometimes when you're cross correlating data, the closest match may not be the right match. Okay, because for example, if you have a data which has, like some work I had done in the past was I was matching Chandra sources to HST sources. So for example, in that case, Chandra had in a particular region of the sky, it had something like 400 sources. But you have, if you see it in HST, you may have 40,000 sources, or in infrared, you may have many more. So there are many techniques which are used to actually cross correlate, not just spatial position in the sense of this thing. What is done is that people match it with other factors also, for example, the brightness and other parameters which can be available. So that is why, if you see what Deborah mentioned is that they actually have code for cross correlating, and the code, the techniques used vary depending upon the wavelengths that you are dealing with. For example, if you're matching X-ray to infrared, then you would have to take different things in consideration compared to if you're doing optical with your infrared, right? So yeah, so if you say if you have a top cat, the matching may be different, etc. With this, it may be different. So it is not a trivial question to answer. So if you can match it with whatever you're using, but there could be issues which you need to be aware of. So but never match it just by doing a spatial match. Next time we'll do ADQL, which is the astronomical data query language. In that also there are certain codes which actually help you to do cross matching. And for example, Deborah mentioned in this also they have some codes for cross matching. Yeah. So any more questions? Please try out this Pleiades exercise which I've shared with you all, because all these data, these tools, it's only when you use it for something will you be able to understand it, right? So please have a look at those things. Yeah. Yeah. Many things are similar to the Aladdin interface, only that there are certain things which are different compared to Aladdin. But all of them come under VO tools, virtual observatory tools. Please write more questions if we have more questions. I'm checking on YouTube. Do we have any questions? But please let me know if you have any more questions. But as a homework for today's class, please try this EsaSky Pleiades thing. It has been explained in a very good way. So you just have to run all the commands as they're given in it, right? Are there any more, Geetanjali? I can't see the tutorial. I've shared the tutorial on the chat window, Geetanjali. So there's a PDF file which I've shared in the chat window. Yeah, I'll share it via Telegram too. Yeah, I'll do that. Yeah, I'll share it in Telegram too. Sure. And it'll be there in the website also. Yeah. You want to start today? Yeah, so before that, in preparation for tomorrow's session, sir wants to talk to you. So he's going to come and talk about the art session. Another question which we wanted to keep as an open question was for next Saturday. Next Saturday is Diwali. Do people prefer that we have class or we don't have class? Please put a yes or a no in the chat box, depending on whether you want class on Diwali or no. We are fine. We've actually had classes on Independence Day, on Dasera, on all days. So yes means we can have class on Diwali, no problem. Yes, okay. So we'll have class on Diwali, no problem. That's a good start to the day. And now sir will talk to you about R, because tomorrow we are going to have a session on R and you'll need to install some things for that.
Hello, everyone. Tomorrow we'll start with R. We asked you on Telegram how many of you are familiar with it, and almost all except one. Priyam said he is a beginner, while all others said they have no knowledge of R. Right? So we will start with R, and then we took another poll whether you want to learn it or not, and then many said yes. right? So what is R? Why do we use it? One thing is R is a open source software which is used for statistics very extensively. It is used a lot by statisticians and researchers. And the competitors for R are SPSS, SAS, Python, and so on. So SPSS and SAS generally are used by social science people. It can be used by scientists too. There's no such specific thing. It does statistics in a very simplified way. For example, SPSS is very similar to using an Excel sheet. But the downside of using SPSS is it is expensive. So is SAS. SAS is used a lot by commercial organizations, but these are expensive ones. R is an open source and free software which you can download and use. So a lot of academicians and researchers, they use R. And Python is again a very powerful programming language which is emerging. And Python is a little more flexible. It can do a little more things than R does. But yes, R is a good choice, and there's no harm learning it. So tomorrow we will start off. Initially, we'll just see what R is. And can you see the screen here? You are sharing a screen, no? Yeah. So, like Priyam has shown, you can download and install R before we start tomorrow. Just uh, either click on the links which is given by Priyam, or you can just go to your Google page and say R installation. And then you have all this in Ubuntu, in Linux, and R installation Anaconda, R installation Mac, and so on. So depending on what operating system you are using, you specify R installation in Windows 10 or Windows 7 or whatever. And then you have this thing, you can download R 4.0.3 Windows. Yeah, so there are many sites. Just click, and for Windows, uh, you just get an exe file which you run it. Okay. So download R 4.0.3 for Windows. It shows 85 megabytes, 32 or 64 bit. So now depending on what your operating system is, obviously you all know if you have a 32 bit operating system, then you cannot install 64 bit. But the other way around, if you have a 64 bit, you can install either of the two. And obviously, if you have a 64 bit, then you will be tempted to install the 64 bit one. So you just click it and you can download. You can see this, right? Yeah. You can download this exe file. Uh, Download this. I think you can't see. Anyway, you download it and run that exe file. Similarly, if you are doing it in Linux, in whichever flavor of Linux you are doing, you say R installation in Mint, Linux, or whichever one, how to install R on Linux Mint. So you have all those, what are the prerequisites, and so on and so forth. Okay. So you have this, like Mint is also a Debian, runs on the Debian kernel, like Ubuntu does. And the sudo apt-get install rbase is a good command too. So first you run the sudo apt-get updates, then you run the sudo apt-get install rbase, And then when it's installed, you can check what version it is, R version, and it will show you what version it is. And you can start the R command using, depending on what operating system. In Windows, it will create an icon on your desktop, or you can click the Windows button, start button, and the moment you say R, it will show you R and you can start running R. Okay. Another thing which people very often do, which I think is not a good idea to start off with, is you can install a R Studio. R Studio. So again, R Studio download. Here, can you see this? So there is this R Studio, which is an IDE integrated development environment. It is the GUI, a graphics user interface with R running at the back end. So you'll have to obviously install R first, and then you'll have to install R Studio. But I wouldn't advise you to use R Studio as of now. Later you can do it. For tomorrow, you just install R, and then we'll use the R environment and work in that. Okay, because this GUI makes lives a bit easier, but let's not get into that as of now. To understand R, it's better to go on the terminal and run it. Okay, so your job for today is to install R. Are there any questions? Any questions regarding any preference which operating system we would suggest? I would suggest use Linux, migrate to Linux as early as you can, but it's your choice. It doesn't really matter. Finally, doing your job is important. And Windows is also good enough. But Windows, as you know, has its own issues. You'll have to pay for it. It has viruses, it crashes, it does all those things. It's a big black box. And Linux is something which is open source and free and stable and scalable. You can run Linux on an older system also pretty well. And we use Linux since 1994 from the Slackware days, and it had been running. Linux has been very good. We had no issues. Which flavor of Linux is good for astronomy? Uh, there is one called Linux, Scientific Linux, but it has Red Hat. Yeah, it is a Red Hat one. See, Red Hat was something which we have used for a very long time. It was very stable until the time Red Hat broke up into Red Hat for uh, corporate and Fedora, which was free. You know, Red Hat was coming with some licenses, and so we started using Fedora. But Fedora is very conservative, so there are many libraries which are not installed. So you have to install things. For example, you are installing R, and suddenly it says it requires these library files. So you have to go and install those. Okay. So in that sense, Ubuntu has become very user friendly. It's easy to install. And once you install, it detects most of your things, your graphics card, your audio, uh, everything runs very smoothly. It detects most of the uh, uh, Wi-Fi, your what is in your system devices. So Ubuntu is a, for people who have not been using Linux for a long time. Ubuntu is easy to install, easy. It detects all your the most of your things on your computer. So maybe go with Ubuntu, and the Ubuntu community is pretty strong. If you have any issues and driver problems installing a printer on it or installing some dongle or something, Wi-Fi community over the years has grown a lot. But Ubuntu is now slowly becoming pretty much like a black box, like what Windows was, and that is bothering some of the hardcore Linux users. Uh, a scaled down version of Ubuntu is Mint. In Mint, again, you have two or three. One is Mate, Mint, Mate. It is slightly light on resources. It runs more smoothly. It doesn't dump in everything you require. So it runs pretty smoothly. And it is doing well with our scientific things. One of our systems has Mint, and Mint is somehow proving to be slightly better than Ubuntu, though it's the same kernel. But like I said, Ubuntu has become heaven for the newbies. Hence, it installs a lot of things, even things which you don't need, and unnecessarily eats up your space. It runs processes behind which you probably don't want them to run. It can slightly slow you down, but this Mate is pretty good. I tried it on one of our old machines. Mint Mate is running very smoothly, and Avik says, yeah. So Sargam, I think so. Linux, they are see Kali Linux is for hackers. Any Linux is as good as any, uh, but Ubuntu is easy for people who have not used earlier, uh, and Mint is a scaled down version of that. Avik asks, if possible, can we take one example problem which we have already seen, like ones in Topcat, and do a statistical analysis of the exactly. Yeah, that's what we will do. In fact, what even we felt was the way the Topcat and in fact the Tim, the way Tim did with exoplanets and all, that's the best way to do for this specific course, where you actually download data and you analyze the whole thing. So that's what we will do with the statistical analysis with R. But maybe before we get down to it, maybe tomorrow we will just have to start from the very beginning, because many people have said they don't know anything about it. So for any programming language, you have to know some very basic things as to your variables, the data types which you use, right? Then the loops, the construct of while loop, do, and just the basic constructs we'll have to know, right? So we'll have to look into the data types. One is, how do you invoke the thing? How do you come out of it? How do you read files? How do you write into files? Yeah, these are the things which are very essential. Then some basic things about how do you plot, right? So we will very briefly look into that, and maybe next we'll take a data set from astronomy specifically, and then, or even tomorrow if possible, if we have time, if we run through the first things very fast, then we can specifically take one data set and then do some statistics on that and do it. Yeah. Can we do spectroscopic analysis sessions too? Yeah, later we'll think of doing that. Uh, at least I'm not familiar with spectroscopic analysis, but we will see if we can find somebody who can do it, or I'll try to look up and understand and do it. So that will go in the third session. Yeah. So if spectroscopic analysis is photometry is what we have been doing all the while. So even Priya is familiar with photometry. Priya, can you handle spectroscopic data? Yes. Yeah, we will try to do the best. Okay, don't worry. Yeah. So and then the whole idea, which I feel with this whole courses, we are showing you all the possibilities, how to get this data, how to get these tools, what are the tools available to analyze this data, and then you yeah, we are introducing you to it, and then you have to get into the nitty-gritty and do it. Anything and everything, right from Topcat or Aladdin or EsaSky or Biostat or Python, when you start specifically working on a problem, that's when you have to learn in detail how to do it specifically for that problem. Okay. So we can't teach you everything, and that it doesn't make sense to teach everything because not everybody needs everything. And right. But if you know that such a thing is possible, this is available, then you get into it and try to learn how to do it. And there are very large communities, R communities, Python communities, all these open source ones especially, who are ready to help each other. Uh, this was stressed by people who are handling Python sessions too. Like Ishan said the same thing. Again, Kastov also said the same thing. That see, these are available. You go on the net, specifically the problem you are looking for, you search, and you get the whole code also. They are providing you the whole source code to do the whole analysis. And then you have to alter it, tweak it for your specific problem. Yeah, so what we shall be doing specifically is how to get into it, how to start swimming, and how do you swim like an expert is up to you to build over that, right? So that's the idea. And yeah, so because the whole each one is an ocean. The more you get into some specific problem, you realize you can spend your life doing that specifically, right? And here we are teaching you all the tools, things which we have learned over years, over months of interacting with people and seeing. And most people are unaware of it. We are making it available to you so that you can build over that. And somehow in India, we don't have this thing. We hide our knowledge. You don't try to show it. But the people who came in with us together, Shoshan or others, Tim, others, they are the ones who are ready to share, tell you everything they know. They are not hiding what they know. They are making it open and telling you, go ahead, do it. So those are the people we got them together, and from here you should build up. Okay. So for today we'll stop, and we'll meet tomorrow. So yeah, Diwali class, people have said they want it on Diwali. So no problem, we'll have it. Okay. We'll have it from the usual 10 to 11:30, and then we'll go and celebrate. Okay, so all the way, anything else you want to ask? Okay, so if there's nothing more to ask, please install R and try to do what Priya madam has given you as homework. Priya ma'am's homework will be for the next Saturday. Yeah. And today's my homework is just install R, and if you have issues, um, ask on the Telegram group, and we'll be ready by tomorrow. Okay. Okay. So tomorrow we will continue with the assumption that most people are novices or beginners at R, but we will not spend too much time in the prelude. Very fast, we will come to actually using R to do what we want to do. Okay, goodbye. How does it stop? Stop sharing.